So I hope at this point all of you have met with your teams. You know, if you haven't, that's an issue. But meet with your teams, set up a weekly meeting time that works for all of you as well as your mentors, and make sure you stick to it, right? It's really important you spend that time together. I also hope all of you have connected with your partners. I think most of you have. I've seen a lot of the email traffic, and it's great. It seems like most of the partners are being really responsive. Has the Ferrari team touched base with,
They were out of office last week, so
Yeah.
they sent emails back and forth.
And they've returned it?
Yes,
Okay, good.
They seem very excited.
Yeah, they are. Yeah. They might have been in an auto show or something. They're away every once in a while, so that's good. Cool. So today, you know, I want to talk about defining design requirements and setting up your strategies, because this is the stage that all of you are in right now for your projects. And what's nice is we have last year's projects to reflect on, and I'll talk about those. And then we're going to do 2 case studies, 2 today, out of my research group, out of 2 of our projects. One on this prosthetic knee project that I've talked about a little bit already. So to start off with, you guys are reading these 4 books, or parts of them, and this last one will be assigned today. But when you're reading these, keep thinking about the content and looking at it through an engineering lens. Like, how does this content affect you? You know, how do you interact with users? How people allocate their income influence what they buy, right? How could you engage new markets through a business, right? And this is really about, like, how could you do more grassroots type strategies. But I think all of these books, none of them I would say are like engineering books, but all of them really influence how we design in developing and emerging markets. So yeah, think about the insights they give you and compare and contrast them. Like, you might read some of these and be like, that's bullshit. Like, you know, and that's okay. That's, you know, I feel the same way, and you should, you know, it's fine to think about that, and I hope we have a really good discussion with Vijay when he comes. Unfortunately, I've been talking to both these guys, and they're out of the country right now. Abhijit came last year, so I'm not sure yet what we're going to do about the development economics. I hope we'll have a good discussion about it anyway. That's in a few classes from now, but I'll try to get some development economics perspective coming into the class too, from somebody coming in. Okay, so some points that I want to stress about when you're defining your strategies and design requirements. I tried to, like, one of the comments last year in the class reviews was that people wanted, I think, a bit more guidance when they were going through the stages and the milestones of the projects, right? And so I think these are kind of my top 5 words of wisdom about where you are right now, and I think the case studies and stuff you'll see in a minute will really reinforce these. But the first is, you are going to need to understand where the motivation comes from for your projects. Like, why are these good projects to solve? Is it motivated by, like, a big social cause? Is it motivated by a great new market opportunity? Is it motivated by some, like, lack of knowledge in the academic community? What is it? And you should be able to say that, and that's going to be included in the introduction of your final paper. The second is, you want to understand that whole stakeholder chain or customer value chain analysis. You know, you read that paper as well, behind your project, right? So you're thinking about end users, but you want to think about that whole chain. And many of your partners represent a lot of that customer value chain, right? They're manufacturers, distributors, you know, sometimes they're getting money from the government, so they know those schemes really well. So you want to understand that whole space. You also want to keep thinking from a user-centered perspective. And I thought Mark did an awesome job in the last lecture, like just trying to empathize with end users. And so you want to, as best you can, and I know you're limited by your physical location, but try to put yourself in the mindset of the end users. Try to empathize with them. And I like the mapping activity talked about in Hidden in Plain Sight. Just kind of mapping out, like, people's days and what they do. You know, you can do that same thing for your projects. You also want to think from a machine design perspective and a technical perspective. So you should be thinking about, like, what's going on in your projects and what that means physically and from, like, an equation standpoint. Like, what dictates power, speed, cost, etc. And you want to understand those critical physical and theoretical relationships that really define your problem. Because it's those relationships that are going to give you insight into a new solution that you can design. And that's a very important part of this class. And you'll see that more in the examples today. And then finally, when you're defining your design requirements, try to do it as quantitatively as possible, right? So for example, instead of saying it has to be low cost, say $10, you know, or if it has to be quiet, say, you know, actually give a decibel reading to that, you know, measured at a certain location, than just saying, oh, a thing needs to be quiet, right? The more metrics that you can put on your design requirements, the better you can actually quantify is your solution successful, right? And you can better define your targets that you're going after. Okay, so some examples from last year. I pulled all these slides from last year's strategy presentations, and I thought they really stressed these points well. So this was from the Bulkey team last year, and one of the first things they did was collect market data on weight versus power, or weight versus pulling force, and to see, like, what does the industry trend show? And how does that compare to where they would want to be potentially with their solution, right? And so they searched around and got all these market data. They also went in and looked at the terramechanics of what dictates how much pulling force you can generate with a wheel, traction force, right? And so they looked into these soil mechanics principles and understand, you know, how things scale relative to each other. And it's like area of the tire and friction angle of the soil, you know, et cetera. And they went and actually read the, you know, sections of the books on this stuff. Another good example was the solar powered drip irrigation team last year. So they tried to contextualize the problem within the global scope of, like, what irrigation can do for poor farmers, right? So tons of water used in agriculture, like in India, which is a water constrained country, and they're quickly running out of water. And how big is their potential market for these off-grid systems, right? So this was good. And they also did this really cool analysis of, if you just had solar panels directly driving a pump, how big a pump would you need, or for a given pump size, how big a panels would you need for different daily flow rates? So it's 30 meters cubed per day, 27, 25. This was their target at 25. So they saw that, you know, if they have a certain pump size and they just get bigger and bigger panels, you get a diminishing return. You can't really put out any more water, really. So they did this analysis and then contrasted it with what they could do if they had a battery buffer within the electrical system. So, you know, they looked at the solar radiance per day and then said, okay, if we take the area under this curve and can store maybe this little bit, and this little bit, we could pump at a constant power throughout the whole day, right? And so they were able to see that with that battery buffer, for a given volumetric flow rate, here's 25 meters cubed per day, they could use maybe like a little over 1 square meter panel, rather than up here, you know, you'd need about almost 2 square meters, right? And that lowers your capital cost. So this is really, really good analysis they did to validate whether this buffering idea, this buffering strategy would even be feasible, right? And this is a really good example of a strategy, because they're saying, hey, we can use this energy that we're not capturing at the beginning of the day where our power's too low, or at the top of the day where the power's too much. We can capture that excess energy and use it to our advantage. Right? When I just explained that, I didn't tell you what the pump looks like, how big the battery was, or, you know, what the physical embodiment looks like, but they were able to validate the strategy theoretically and show that it had a lot of promise, you know? And they're now, like, turning this into a startup, which is pretty cool. Another example was the drip filter team. And so I pulled this slide out because I think this really nicely puts quantitative design requirements on the problem. You know, look at all these numbers, like the system size, you know, what sort of contaminant types there are, very fine to medium sand, and they've got the particle range, you know, they got price points. It's really, really nice. And then this is a soil type map of, I think, Ghana, where they were working. And then this is a bunch of different ideas they had to take particles out of water. to filter it. And so they're talking about gravitational settling, centripetal, winging the particles out, and the force balance that the particles experience as they go through the tube. And what I liked about this is they looked at like how these factors scale with each other. So you can see a bunch of arrows here, like as something goes up, another thing goes down. So they really looked at the physics of all these solutions. They actually didn't go with that strategy. They went with more of a conventional filter strategy, but they still worked out all these physics, which is really cool. So today, we're going to give you a rundown in greater depth of two projects that I think really highlight how you bring together technical and socioeconomic to define a strategy and see like a solution path. So I'm going to hand it over to Natasha first, who's going to talk about her research on village scale desalination, and then I'll talk about our all-terrain knee project. And this class, I meant it to be, like hopefully we finish with about 30 minutes left, because I want us to have a lot of discussion about your specific projects and maybe questions you have about how to do this.
Yeah.
What? No, it doesn't show up.
Okay, so my name's Natasha. I'm one of Amos's grad students, and I'm working on a project with Jain Irrigation, which is an irrigation company in India. They're the largest producer of drip irrigation systems in India. And essentially, they approached Amos 2 years ago with this question about how they can impact the water market. And so the first thing we talk about is just very briefly what the problem is. As I'm sure a lot of you are aware, there are a lot of villages in India. It's 75% of the overall population. That point of use and community scale-based systems are currently not meeting the need for water purification. There's still 11% of the population worldwide without access to an improved water source. And what's important to look at whenever you look at, this is a Millennium Development Goal statistic, when you're looking at that is to look at what improved means. So further, that improved really only means that you have a household tap or a public standpipe or a borehole. So if you consider the fact that the borehole might also not be clean if it's not covered or anything else, consider all of that, that there's actually an additional 1.2 billion that the Millennium Development Goals aren't considering as being covered with safe water. And that you have even further difficulty reaching areas that are off-grid. So Jain Irrigation saw this issue, and they kind of posed this question to Amos very broadly in that how can we enter the water market? They don't currently do anything with water treatment. And how can we have a positive impact on this bottom of the pyramid market? So that's where I entered. That's a very broad question for anyone that's worked in water. There are a ton of different purification technologies, and it all depends on what water quality parameters you have. And so the first thing we look at is, well, what are people currently using? Currently in India, 73% of the rural population is not treating their drinking water. Of those that are, you can see that this column here says straining through a cloth. That's usually like a sari cloth. So usually if it's only done one fold, you're not actually removing anything. You're making it look cleaner, but not actually improving water quality. If you fold it multiple times, you can remove some of the bigger contaminants, but it's still not everything you need. And so if you kind of remove that, you actually have closer to 90% not doing any water treatment. And so the question is why? Because as you can see, all of the normal like home water purifiers that we think of as on the market, I'll talk about in a second, those all fall under just one of these categories, this ceramic, sand, or other water filter, and less than 5% of the population is currently using those. So why is that? So one thing, I know there's a lot of data in here, so I'm just going to point out specific things. This is a comparison of different technologies currently being used in India to treat water in bottom of the pyramid markets. So the first is simply just a chlorine tablet. It's extremely cheap. You can buy a single dosage. That's part of why they're popular, because often you have like very small disposable income, so you can buy them in a single usage. But if you scale that up per dollars per meter cubed of water produced, you're still spending nearly $2, between $1 and $2 to treat your water. You can also buy a variety of different home water systems. This is a stainless steel gravity filter. Most of these filters, are yay big. They have two compartments, a top compartment for dirty water, some sort of filtration device, and a bottom compartment for safe water storage. All three of those have that same type of system. One uses, these first two both use clay, which is inexpensive, and the Tata Swatch uses rice husk ash. Both of these, if you, again, scale it up over the lifetime of the product and per dollars per meter cubed of water treated, are quite expensive. Obviously, bottled water in private tankers are ridiculously expensive. You never make that a sustainable solution, but often people are forced to do that, which is why it's there for comparison. So if you look then at what you could do with a potential community scale system, so there's two things we're looking at here, community and what particles are being treated, and you scaled it up to this 1,000 liter per hour, so 1 meter cubed per hour system that a company called Tata Projects is working on, you can, for a similar price range, actually desalinate water or remove a lot more particles within the same price range. And so perhaps that's a viable technology. So before even, I know some of you, or hopefully all of you, read the paper that was posted. Before even getting to the paper, this is kind of some of that further background work that was done. And so part of the question was, are we even looking at household water purification, or should we look at community-based systems? And so there were a variety of problems that I personally saw with household water treatment, and that has been backed up in literature as well. The first is that there's minimal economy of scale, as shown in the previous slide. So if you actually give every single family in a 300 family village one of those steel filters, that's $25 at 300. You actually pay more than you would to give them a desalination plant. And I think often NGOs don't think about it in that context. Additionally, that health improvements has to equal safe water plus consistent usage. So a lot of these systems provide an outlet for safe water, but if the user is not using it every single time they ingest that water, it doesn't have any health improvement. That means that behavior change is required. And anytime you require a behavior change, your solution is orders of magnitude less likely to work, essentially, unless you have a very good educational campaign and everything else that goes with it. That leads to poor adoption, so that's why some of these filters are only being used less than 5% of the time. There's also cleaning and maintenance requirements that come along with any water purification technology. And when you're requiring that an individual do it at the household level, it's much less likely to occur, which leads to quality control issues of the output water. So in field tests that have often happened, you can collect water samples from each of these household systems. They're usually not adequate, essentially. And then lastly, kind of when we talk about meeting with people all along the stakeholder chain, that it actually doesn't fit within Jane Irrigation's key manufacturing strengths. So they make large extruded pipes, they make solar panels, they make large scale systems, and other than their small solar lanterns, they don't really do much with this commercial product side, or consumer, products. And so all of these things led us to focus on community scale water purification systems. And so this kind of became the new goal statement from which the paper jumps off of. So this is a summary of the different things that I'll talk about in the talk, and that was also given in the paper. Essentially, we use a variety of facts found in literature as well as in interviews to define why desalination is required, why PV power makes sense, the really big importance of recovery ratio, and as well as the energetic and system cost analysis. So the first thing to consider if you haven't looked at water stuff before is that there is a very wide spectrum of contaminants, and they all have very different sizes. And different sizes means different energy or power requirements to take them out. So starting on the right, you have large particles like algae and bacteria, all the way down to dissolved salts like sodium chloride on the left. As you move from right to left, the particle size gets smaller, and as a result, the pore size of any sort of filtration device would get smaller, and as your pore size gets smaller, your energy and your power goes up. So this is part of the reason that most NGOs try to stick on the right side, because this is also where most of the health effects come from, right? Diarrhea is caused by these things on the right. So why not just remove the bacteria, because that's what's causing the health effects, and it's cheaper to do so because it requires less power. And part of the question of that is you have to look at what users really want in their water purification device. So based on both interviews done in Maharashtra state as well as a variety of different literature sources, we know that people don't actually judge, in this situation, people don't judge the quality of their water or the healthfulness of their water based on what's in it. They judge it based on what it smells like, tastes like, if it's cold, if it's hot. And we do the same thing. If you turn on your tap, or if you go to a water fountain, it smells like rotten eggs, there's certain things about it, you don't drink it. And even if it's perfectly clean, you still won't. And this is the exact same thing. They describe in interviews good quality water as being safid, which means clear, and mitha, which is sweet. Sweet in this sense is in the opposite of salty. So they find bore well water to be salty. And so some of these things initially led us to believe that salinity is an important aspect of water quality, or water aesthetics, and perceived water quality. So that's only really important if salinity is an issue in the target market, which is India. We know that it is. This is a map of India with the different salinity levels, with this high red regions and spattered down here being greater than 2,000 about ppm. ppm stands for parts per million of dissolved salts, where the green and yellow regions are a little bit less. However, anything that is green, yellow, or red are all above the taste threshold. So what this means is that you end up with 60% of the land area in India having a salinity level above that which users can taste, in which the water source is likely rejected. This is also similar if you look at the global water spectrum of what's available on the earth, right? We know there's only like 2.5% of fresh water. If you look at groundwater, there's about 50-50 split of groundwater that's salty and groundwater that's fresh. So that is only important if users in India actually get their water from the ground. If everyone's using surface water sources, that's again, it doesn't matter. We find that it does matter though, because you can see if you combine all of these public standpipes, which is groundwater, tube wells and boreholes, unprotected dug wells, all of these three top columns here, here, and here are all sources that are used groundwater. So we know that there's a lot of salt in the groundwater and a lot of people are using it. At least 70% of the rural population uses some form of groundwater. Additionally then, if you say, well, India has 15% of the population and only 6% of the water sources. It's also, there's a lot of desert regions, so water scarcity is an issue. You can look at water scarcity maps of India and say that there's vaguely these regions, boundaries are a little bit fuzzy to change, but this orange area and orange area below are areas that are already in physical water scarcity, which means they're removing more water than that's getting replenished or are approaching that. And the economic water scarcity in purple simply means that infrastructure or other economic political reasons are inhibiting access to water. So it's called here economic water scarcity, but there's different terms for that. So we know that maximizing the recovery ratio of the system is important. What recovery ratio means is that how much water you put in, you want the most of that out. So if I have a recovery ratio of 50%, then if for every meter cubed of water I put in, I get half a meter cubed of water out that's clean. And the other half is pure waste. So if you have an area that is very water stressed, you want to maximize the recovery ratio. Similarly, you can look at what system size we're talking about. So you know that 60% of the Indian population is living in a village of less than 5,000 people. So this information you can just pull from the census. And at 3 liters of drinking water per person per day, you get a system capacity of around 6 to 15 meters cubed per day. And why that's important is that once you start looking at these desalination technologies, the size of your system matters greatly for what makes sense of which technology to use. So again, and then if you look at energy sources, we know that approximately half of village households in India do not use electricity for lighting. Now that might seem like a really odd statistics to use to define who has access to energy for water. But the reason is that if you actually look at village electrification data in India, they'll tell you the number is way too high. They'll say the number is like 95% village electrified. But the reason for that is that they do, essentially the marker just changed. This is kind of back to that indicator thing again, where the indicator used to be that one household in the village had to have electricity to be considered electrified. And so if you consider this, essentially the statistic is a lot more, it tells you a lot more about the actual accessibility within a village. If every household has access, if it's just occasionally. Usually if only one household has access, it's the chief and it's not really available for use by a water plant. Additionally, if you look at literature studies of small-scale desalination plants, we found that solar is more cost-effective than diesel generators. That's been cited in a few different papers. And then obviously that solar is a huge energy resource in India. So we kind of filled out this part of the chart, and in order to determine our last blue section to decide what technology actually goes in the middle, we have to look at energetic and system cost analyses. So there's a variety of different desalination methods. I'm not going to go into all of them, since I know that's probably beyond the scope of this. But on the left, you have membrane technologies, anything that uses a physical membrane either to pass water through it or to do the exchange of exchange of contaminants. And then thermal systems, which is essentially using heat in almost all of these cases, heat to evaporate the water and then condense it. At these small scale systems, so this is kind of where it goes back to why the system capacity matters. Generally speaking, everything below the first line here, MED, MSF, et cetera, are only viable at systems around 6,000 million gallons per day or greater. So you would never use this for a small village system. Distillation, you can talk about little solar stills. The problem there is if you actually calculate it and do it for a whole village, you're looking at acres of land covered in solar still. And so that's also not viable. That's kind of a middle ground, I guess. So we're going to look at two technologies on the left here, reverse osmosis and electrodialysis. Reverse osmosis, hopefully remember from one of your chemistry classes what osmosis is. So that's water from a low salinity stream going through a membrane, a semi-permeable membrane here, into a high salinity stream in order to balance out essentially the concentrations. When you do so, you end up with an osmotic pressure difference. Reverse osmosis is doing the opposite. It's applying a pressure to that high salinity stream to force it to go the other way. So the pressure you apply has to be greater than the osmotic pressure of the salinity stream. Some of the governing equations, if you were to do a first order cut at this, you can say that the osmotic pressure is a function of the molality of the stream, and that the specific energy is a function of the applied feed pressure, as well as some efficiencies of your pumps and motors. One thing here to consider, though, is that for these low salinity streams, so like too high of salinity to drink, but still low salinity in comparison to seawater, that the applied pressure is greater than the osmotic pressure, but it's actually even greater than that because the osmotic pressure is fairly low at these cases, and so you're actually applying a pressure that's has more to do with the flow rate through the system than the osmotic pressure. So anyway, that's just a side note in case you're wondering where the numbers come from later. And so the other technology we'll look at is electrodialysis. Electrodialysis is a system when you have a saline feed water up top. There's a variety of ions spread throughout it, positive and negatively charged. You apply a voltage essentially across an anode and a cathode, which is going to generally cause your anions or the negative charges to go towards your anode and your cations to go towards your cathode. When that happens, however, you also have this system of alternating membranes. So CEM stands for cation exchange membrane. AEM stands for anion exchange membrane. So you have an anion that comes down. We'll follow it here. It's attracted towards the anode. It's allowed to pass through an anion exchange membrane, but it gets blocked by this membrane, which is negatively charged. And the opposite happens for the cations. You have a cation that comes, let's say this one, that comes down this stream. It's attracted to the cathode. It gets through the cation exchange membrane, but is blocked through the anion exchange membrane. What this results in is alternating channels of high concentration streams. So here you have your concentrate in the middle, and low concentration streams are your diluate on the outside. So if you look at the energy consumption of a single stack like this, you have one cell pair which consists of two channels and two membranes. You can look at it kind of like an electric circuit, so you have resistance across each of the two streams and the two membranes. And you have a voltage across it, which is given by the current density in amps per meter squared of membrane area times these resistances. There's also some other voltages in there I'm not going to get into. But essentially what that says is that your energy scales with your current and your voltage, or it's the integral of that power over time that it's in the system. And that we know that as the resistance of the system increases, that the energy is going to go up, which means that as you desalinate the water and the salinity gets lower and lower, so you start with 3,000 ppm, but as you're bringing it down to 500, that your power consumption, those last few stages goes up. So if you look at how specific energy depends on feed water salinity over the range found in India, so here we see feeds water salt concentration from about 1,000 to 4,000, which is the area of interest, versus the specific energy kilowatt hours per meter cubed of water produced. There is a line for reverse osmosis, electrodialysis, and least here just represents the thermodynamic least number. We don't have to worry too much about that. So essentially, it tells us that within the salinity range in India, electrodialysis is more energy efficient. You can also look at it from a system cost analysis. This now is over a much wider range. So this is based on a paper done by Strathman in about 5 or 6 years ago. But essentially, there's a feed salt concentration from here 1,000 to 100,000. This is in PPT instead of ppm. And so the range we're looking at is just this range here on the left. And again, though, you find that in the range that we're interested in, electrodialysis, even from a cost perspective of capital equipment, et cetera, is usually less expensive. Now these, you have to understand, is also very based on the scale of the system. So this is usually for large scale municipal type systems. And so how these scale back for village scale systems or home scale systems is what I'm looking at in my research. So Tata Projects, the 1,000 liter per hour RO plant that I talked about earlier, they have almost 600 of these, or probably now 600 of these installed. They are on-grid plants, so they do use the village electricity supply. Usually that electricity is only available for about 5 hours per day. So that means that the system is oversized in order to meet that demand. And have a recovery ratio of only about 40 to 60%. The cost of this system, if you break it down between the plant itself, as in what was just shown in the picture, versus the shelter, storage tank, wiring, the bore well excavation, all of that stuff, you find that, and then if you move it off grid and try to make it PV powered, you find that the power system is more than a third of the cost of the system itself. And so what that means is that right now they've sold these 600 systems on grid because they can get banks and whatever else to give them loans to get these systems out for a short payback period. But as soon as they move it off grid, it's no longer economically viable. So this is kind of our target price point. We know that essentially this number, these first two rows, if you add those together, we know that's viable because they've had success installing these and scaling these up. But once they hit this price point, then that's not viable. So our target price point is the first two. Yeah, and that the solar power system is expensive. In addition, you can look at maintenance and functionality between the two. There's a lot of information here, but essentially some of the key points that were important to our decision is that electrodialysis has a much higher recovery ratio, closer to 90%. The membrane life is longer, which means you have fewer membrane replacements. In general, because RO membranes have a really sensitive membrane, essentially, you have to do a lot more pre-treatment of RO membranes. RO membranes can't handle high levels of chlorine. So in some of these villages, the water has been treated by chlorine by some municipal level, and often really high levels of chlorine because they don't really know how much. They just kind of dump it in and make sure it's fine. And those chlorine levels are way too high to use with reverse osmosis. So you have to remove the chlorine and then put it through RO. Versus an electrodialysis, you can actually use the electrodialysis itself to remove the chlorine. However, on the flip side of that, we know that the capital cost of ED membranes is significantly higher. And so that's kind of the economic trade-off. So one thing I'm looking at now, just to tell you where this project is going, is whether PV can be, or electrodialysis can be driven directly off of PV. So as you can tell from the kind of the system schematic I drew, it takes a direct current, which is what PV panels produce. And so there kind of seems to be a natural relationship there. And so whether you can actually remove the batteries or not and drive it directly off of the PV panels, or remove a lot of the batteries, so that in and of itself would remove some of the cost for an off-grid system. However, even without that, we know that since it requires about 25 to 50% less energy, even without removing the batteries, we feel that the power system in an off-grid setting would be about 50% of the size. So that's kind of what led to this, I guess, artsy schematic of our decision to move forward, at least investigating PV-ED as an option. We have an experimental setup in lab that's looking at some of these just to kind of show you what it looks like. You have some buckets, some 3 pumps, and a little mini ED stack in here. We have a model, experimental results that are kind of showing the dots here are the experimental, the solid lines the model, showing essentially what we're looking at. And then also showing that you can direct drive the system from the solar panels that Jane already makes. So that's kind of the types of analysis we're doing now. But there's also some difficulties with it. We know that optimization of current and voltage trajectories is difficult in a direct drive system because if you were to actually just connect it and you didn't have any switching between making the current voltage or the voltage current, essentially, you wouldn't have your ideal system. So there's going to have to be some sort of playing with the power there. And also, I guess, optimizing how much battery versus how much solar. Sorry, I'm actually going to skip that part. And then another thing from the kind of, again, looking back at the system requirements is that we know there's an extreme annual variation in solar radiation. I'm giving an example here for Hong Kong just because I have the flip information that I'm trying to show. But essentially, we also know that there is annual variation in water demand. And so if you overlay that map of annual variation in solar radiance on top of the annual or the daily water consumption map throughout the year, you find that they actually line up pretty nicely, and that's true, has been true in a lot of different studies in a lot of different cities. And so part of the question as well with direct driving the system is you don't have to oversize it necessarily for the cloudiest day if on the cloudiest day you also drink half as much water. So those are like some of the other aspects we're trying to work with other NGOs working in villages to find out how true those trends are and how much we can use them to our advantage. Yeah, so essentially we identified this opportunity for small-scale desalination, system design requirements, developed an analytical model and experiment, and now we're moving forward with optimization of the system. So that's kind of where we are and how it started really broad and got narrowed. Should I do questions now, or you want to wait till the end? Okay, yeah, so you can ask me questions. Yeah.
Your overlap chart you just showed,
Yep.
is that because of the rainy season?
In Hong Kong?
Because people can collect the water and that's why the consumption?
Yeah, so in each city it varies as to why. Part of it is purely the temperature. So you drink more water when it's hotter than when it's colder. So part of it is like directly correlated there, and then part of it is with the rainy season. So people collect it or whatever else. I mean, it depends on the city you're in. And that's part of why we have to investigate further with a specific village or region that we're interested in implementing, if that's still true or not. Yeah.
How long, you mentioned Jane reached out 2 years ago. How long did it take to set those system requirements and those functional requirements?
So we got to deciding to move forward with PVED probably a year. The last year has been more in the system modeling, moving forward optimization. I've been to India 5 times now, so like a lot of those first 3 trips was all meeting with different parts of the stakeholder market.
I think one thing you have to keep in mind with these presentations is that they're would ideally depend on what else might be accessible. So if they're close